After that, who's presented after group 2? Where group 4? 4? 4, okay. After that? 10? 6? You're number 3? Okay? You're number 4. Yeah, group 9, number 4 in your presentation. And then group 1. No. Group 1? Not here. Very good. Yeah, that's you. Okay? My group. Alright? Alright, go. So remember, you don't have, get ready. They finish, you go. Show your eagerness, your professionalism, your readiness. We'll try to keep the question also short. Since we question many times, so we'll go just to the line.
Doesn't matter, sun is zero. Stopwatch. Alright, this is Flexible Field. It's a real world rehab solution for risk-affected people. First of all, most rehab centers are located in the city centers of Malaysia. The ratio of its therapists is only a quarter of what who recommends, and the products on the market are already either too expensive or they offer no real protection against self-harm. So either they're free weights, which you can see in the next slide of the benchmarking. Yeah, you've got the professional devices, which you can see the price is at 372 ringgit, which no rural family is able to afford. We've got the free weights that are commercially available, and but they offer no real support and no real protection against improper form. And in the end, you can see what our first prototype is. We are benchmarking against cost, which you can see the weights and our device is cheap, and we're benchmarking against with the resistance profile, the portability, the manufacturability, and the self-protection. So these are very important key marks that we require, that the rural people require from our product. This is the design idea. We structured it as a modified constraint-induced therapy. This is basically the key commandments is it being affordable and portable, mass reducible. It would be a plus, lightweight, compact, and have varying levels of resistance, and so on. Go ahead. Go ahead. So these are the compliance metric, compliance authority, which is we need to have it registered with the medical device authority. We also need to have it be registered under upper range of motion exercises. Go ahead. So the design spec table, we need the first user need, of course, is that it needs to be structured incremental exercises to rebuild strength and mobility. From it, we need 3 attributes, which is rigidity, durability, and variable resistance. Those are required to achieve the user needs. From the engineering targets, you can see the required. Ultimate strength or yield strength. In our case, we're using yield strength specifically for the case of wood. In durability, we have about 50,000 cycles of durability. That is what is required to finish the entire physiotherapy run, which is assuming 4 sets of 8 to 10 repetitions done daily for 2 years. 6 months to a couple of years is the range of time it takes to fully get up. In variable resistance, we need to be in the range of 0 to 6 Newton at 10% increments. Go ahead. The second user need is that it needs to have address stiffness and scar tissue, basically regain range of motion, and for that you need a progress tracking capability so you can know when how much range of motion you currently have and how much you've progressed throughout your physiotherapy. And the target for that is having a 0.5 degree accuracy. And have a range of negative 90 to 90 degrees. That is regarding the measuring device. Go ahead. The third user need is have it be an easy tool, an affordable tool, and also a very portable tool. So the design attributes is it being cost effective and compact. The cost effectiveness we are aiming at under an under 90 ringgit cost, and compactness is enough for it to fit in a standard backpack, which is 50 centimeter height, 35 centimeter width, and 20 centimeter in thickness or depth. Go ahead. And the final one is safe to use. We needed to have a safe material. We've used basswood, which has zero odor, zero cases of irritability to the skin, and so on. It has to have mechanical integrity, which we have set as safety factor of 2. It requires economic safety, which this is where the medical device, the governing body that we referred to, that's where that comes in, for the economic safety specifically. And the instruction of safety, which is we need to provide detailed instructions and so on. Go ahead. You can go ahead. We could just go to the for the structure. No, that one previously. Yeah. So as you can see, we have assumed the weight to be the average Malaysian weight, and the percentage of the total dead arm weight is 10% of the total body weight, and that's where we started from. That 6.65 kg is the weight of the arm of the average arm in Malaysia, and from that we were able to calculate the bending stress due to the transverse load, bending stress due to moment, and so on upon the combined stress, and from that we assume the thickness of half a centimeter or 5 mm, so that we can comply with the portability, so that it can fit within the dimensions that we had. And from that we got the material properties, which is 14.65 megapascal of yield stress. Go ahead. This is a short video of us prototyping or creating the current prototype that we have. This is the first design verification card, which is the incremental exercises. We're trying to verify if we're able to achieve the range of resistances, as well as the incrementation of those resistances. We would regard the process of working if we can reliably obtain different increments throughout the whole 0 to 56 Newton range. The next one. Okay, there's one of the slides not there. That is the force measurement that we were able to obtain to get the resistance. Go ahead. And that's the progress tracking capability, which is we need to use an external angle measurement tool to verify if our system can reliably measure the angle and so on. In the end, we were able to produce the range of resistances, but we're not able to get reliable increments, as well as we have not had we unfortunately have not had the time to be able to implement the progress tracking capability so far in our prototype. Our future suggestions is that because it took us way too long to get just the base setup going, we recommend ourselves to work with additive manufacturing more so that we can have better and more high fidelity features in our prototype that we can use. Go ahead.
Okay, can you go back to, first of all, overall, it's like you're not ready this time like last time. You can show that the presentation, you know that. And then you put slides, what's the point of putting slides and then next? Then no need to have them there. Doesn't fit with. Anyway, that's for presentation, you have to improve that one in the future. So if you know that you're not presenting, just don't show it. Anyway, Now, I think we went through
Yeah.
this before. So now, from the engineering targets
Yes.
that you have there, which one you are able to show or to prove or to measure, to achieve basically?
The structural rigidity, which is basically use the proper get the material spec correct.
This one. What is the verification for that?
You can't. It's obtaining the material spec. So the verification, the only way would be to take a sample of the material and go verify it in the universal testing kit.
No, but it shouldn't be that one to find it. Because here, if you go back to that one, your design analysis for that, you have only one target
The first.
that you cannot give the concept, etc. Try to measure that one, right? Only one.
Yes.
Okay. So this one here, what is your engineering target is?
The material property.
How is that engineering target? And then you find it at the end as your outcome?
We're trying to find what material is suitable to create the whole structure. Based on the dead weight of the arm being rested upon the device.
Yeah, the engineering target should not be the material, it should be the whatever material you have to choose in order to support this one, which is, so your engineering target actually is 665 kilograms. That is the weight of the arm, right?
Yes.
That should be, I think we mentioned last time, but anyway. Because this, it should be whatever, it can be not many material can maybe achieve that one. But basically, I want to have that one, the 665. That's why you start from here, right? So you find the load, then you find out the moment, and then you need to find the cross section or something.
No, we just wanted to find the material property. We started with the user need that for it to be able to handle the human body. That's the human need. It being rigid enough just to handle the arm.
Okay.
And from that we got the average arm weight. That's the starting point from the user need. And then we continue to get the material property, which is our engineering target, that satisfies that user need.
Anyway. No need to add. Any other points you need to achieve from the design specs?
The factor of safety we were able to obtain, but that is the same thing, but just doing it in reverse.
Okay, so can you operate this one?
Then you can adjust the resistance by pulling this.
Use it to climb
At the end you build it, but now you cannot verify any of your test card, basically, right?
Yes.
This is a full scale model.
Yes.
Because it looks a bit small. Because you are supposed to really support the whole length.
No, we're supposed to forearm. The weight of the weight up until the shoulder, but we're not holding your hand full arm length. As in the support happens in the forearm, however, it can maintain the weight up until the shoulder.
Right, so then, from your prototype, what can you prove? Any concept? I think basically that is what the Professor is asking currently. So you just verify the
Structural stability and it being able to produce resistances in the range of 0 to 56 newton.
So what is the slide table? I think it's a verification for the arm.
That one, yeah.
This one, yeah.
No one has
The slide before.
And that's design the prototype. This is us making it.
And also this is for the resistance band. So this is for what?
This is just making the prototype. You mean the one after that one is for the resistance bands, yeah.
Like you measuring whether it reaches 0 to 56 Newton.
Okay, so then what do you get here?
One. It's only like 30%.
It's upside down, so what is that?
1.3 kilo. So around
139.5.
yes.
So is that achieving your engineering target?
No.
It should be what?
56 Newton.
Zero from the radius is
It's from 0 to 56, so it's like
That's why we got 40 Newton.
1.3.
Okay, so what went wrong here? Because of
Inappropriate resistance bands. You're not able to procure the ones you require.
okay, may I know what the reason? What is the reason? It's not available now, we don't have much time, or?
We going for the cost, so we thought like, oh, maybe like it's cheaper. Open like this one, this is like the office side, one can achieve it. So at that time we finish it and then say, okay, so our cost is dragging out the process instead of
So maybe after this you can do
we
your
can do
start,
with the silicon.
right, and then change the material so that you can achieve your engineering target, okay? Any other questions?
The movement that you can do is just pushing. Is pushing only, right?
Pushing, yeah.
I thought it will be
Both
few direction, right?
You could change the direction of the resistance band. You could place this at the bottom and run the resistance band at the bottom. So you get the opposite direction as well.
Okay, so it can push and it
Yeah,
can
you
pull.
can push in one exercise and then the next set you can do the pull exercise.
Okay, and how about
That would require
this kind
different handle that we have not had the time to
the plan was it has
both. The plan was that we were
Like the attachment is just only like the top of this will be
the handle, change the handle you mean?
yeah, change the handle, just put it.
Mm.
But it will require wood working, so wood is
It's okay, it's the first prototype. Okay, thank you.
Okay, you have 1 week to improve for the exhibition, and it is not acceptable combination. Okay?
Please you have it there. Where's the next group? Group number? 4. Come on, group 4.
Okay, I'm doing a roll call while group 4 is setting up. Kakurazi, are you here? Need Muhammad Aswar. Muaz. Haris. Muhammad Amin. Okay, group 5. Where is group 5? Zairul Aiman. Not here. Islam Sazida. Ahmad bin Anwar. Raja Muhammad Amjad. Not here. And Muhammad Hakimi. Okay, group 7, Alia Sofia. Shazan Nabila. Cik Lutfi. Who else? More Jasmina and Putri Elisa. Both. Group 8, Putri Shania Nabila. Wan Fisha Dania. Mariatul, Nur Aina, and Aida Farisha. All here, right? And the last group, group 10. Group 10 right here. So, all 4, right?
That's 6 minutes. Beliau baru nominate beliau baru kita. Please start now.
5 minutes for setting up. We should have 5 points detected. At least.
Okay, start now.
Ladies and gentlemen, this is not about fun. This is the future of Malaysia and country. It's not a strange device, but it's a device that will lead Durian, the king of food, to the top of the world. So we introduce to you smart dispenser. So what is our problem in durian orchards? Basically, durian farmers struggle to effectively eliminate insect pests, leading to crop damage, reduced yield, and also lower food quality. We have control method, which is traditional method. Number one, we have manual spraying and also passive hanging. Both of them in studies shows that they fail to fight the pest control. So our solution is automated smart pesticide dispenser for durian orchid. Our solution will using AI powered automated pesticide spraying system that eliminate insect pests with precision while reducing labor and chemical risk. So the impact is that we know that Malaysia have 1.14 billion export, so we want to maximize the profit, and our target user is medium to large scale durian farmers. Next, so this is our benchmarking table. So based on 3 things I said before, that is traditional, hanging, and also smart dispenser, we are the best. So for pest elimination, we hide to kill the pest. Usage, we use the lowest, and also centralized, but maintenance, we is the lowest. So, and the best part is we follow the regulation of pesticide guideline and also Malaysian pesticide called MPD regulation. So that's the best part. So this is our design specification. 3 things for myself. First, pest elimination. Second, reduce pesticide usage. And third is centralized maintenance. So our initial target is to reduce by 90% pest. Number 2 is to reduce pesticide usage by 30% and also reduce the tree management by 60%. So this is our system architecture. On the left side, you can see this is the mechanical part. So we have pump, we have tube, pipe, and also we have a nozzle. All of that we calculate and we later will see the calculation. And on the right side is the electric part. Basically, we have 2 circuits. On the right, which is the pump, the circuit of pump will be controlled by the relay, which will be controlled by the SP32, whereby we put a PC module, which is the time clock. So in the rural place, we still can use our product. So this is the calculation for pesticide reduction by 30%. Number one is we calculate how many trees in 1 hectare, because based on research by Yang Samud, a Thailand researcher, a lot of horsepower use 496 liter pesticide per hectare. So after 30% reduction, we get that per tree, we get 2.57 liter per tree. So this is pesticide reduction. This is the pump horsepower we calculate using the Bernoulli headform equation. So we get that pump we needed is 49.06 watt, which is 0.067 horsepower pump. And last but not least, this is for tube, which is we calculate the maximum pressure that a tube required. So that, and the maximum pressure is 101,374 Pascal. So that's the maximum, and we need to find something that beyond that. So this is our validation. Our test number one is to achieve 90% pest elimination rate. Emphasis utilizing our solution to see if we can eliminate pest by 90%. So what we do is we do apply our solution within selected areas within confirmed pest infestation. Next. So we do you have video? No, we don't have video. Okay, never mind. We see the table. This is the result for our test. So for test number one, we use 5 cricket. Cricket 5. So we get all of them die. And for test number two, we do 10 insect, and number 3 we do 20 insect. And you can see the percentage of insect die. And next, this is our test number 2, which is pesticide reduction by 30%. So what we do is basically we apply pesticide using our solution and record how much volume used for the whole process. So for number 1, this control volume is basically the traditional method. So the value is 3.67. This is based on the case study by Yang Samud just now. So yeah, for our product, we get reduction to 2.479 for test number 1, which is percentage to 33%. For test number 2 is 2.368 final volume, which is reduction of 36, and number 3 is 2.516, which reduction to 32%. And last but not least is reduce tree management by 80%. So basically, what is meant by reduce tree management? We compare the time taken between traditional method, whereby traditional method we compare the time taken to conduct for 1 hectare, and we compare to our solution. So this is the test. I'm sorry, not 1 hectare, but for 9 trees, because our system cover 9 trees. So for test 1, time taken for our solution is for 9 trees we cover 3.67%, 3.67 minutes. But the definition they need to use 80 minutes. So we can reduction of 80%. Number 2, test number 2, our time is 4.88. The initial traditional time is 15.8, so reduction by 77%. And number 3, time taken for us is 4.3, and time taken for traditional method is 60.7 for 9 trees, and reduction is 75%. So we so it is 80%. So look at it. This is our prototype. So we put the container same distance of each tree, so 8 meters. Can you see the sure, next slide. So this is our just prototyping process. So thank you everyone.
Okay. To groups to not listen. Your problem statement, we talked about it on progressive presentation. What is the problem? You go to your slide problem statement. And you don't adjust that before I go even deeper. Okay? Effectively eliminate insect leading to the. So what is your problem statement? Can you tell me what is the problem? Effective?
Assistance rate.
Yeah, but what is your thing? What is the problem here? Is it insect? Too many insects? Because later, based on this one, now if you go to your design spec, I want to see they match. Can you go to your design spec? Spec, the table. Okay? So here, achieve 90% pest eliminate rate. Okay? Pesticide reduction by 30%. Okay? Related to also pesticide. Reduce tree management by 80%. What do you mean by tree management?
So the time taken for farmers to settle to manage 9 trees. Because our system is 9 trees, so we want to compare with the traditional.
Where did you get 9 trees from?
Because our design is 9 trees.
How? Why you design 9 trees?
How big is the coverage of what you mean by 9 trees? Coverage is
Why not 10 trees? Why not 20 trees? Why you pick 9 trees?
So 9 trees, basically we from the video that we watched, the pesticide dispenser we could settle.
No. This is related to your solution. At the first thing, you designed it for 9 trees. How did you pick 9 trees? From where it came that 9?
So at first place, we want to reduce the time. So I said earlier that for 1 hectare, farmers need to do 1 to 5 repetition. So 1 to 5 trees. But we want to reduce that. So we just pick number 9. And if we pick 9, they can reduce from 1 to 5 repetition to just only 60 repetitions. So
What is the user need here?
to kill the pesticide.
Yeah, okay, that's fine. That one, you heard the first, the first one. To be 90% eliminate the rate. I give you that one. After that, it's reduction by 50%, tree management by 80%. How you get that number? The 50% and 80%, where did you get them from?
From the validation.
Not validation. Here it's design. It should be the design requirement first. The engineering target. Validation later to see if you achieve those or not. But first, who decided on those 50% and 80%, and what does that mean, that 150%? Because we say pesticide reduction by 50% compared to what? To use on 1 tree, on 2 trees, on a hectare, on 10 hectares. What's the user is doing?
For the 30% we are using for a tree. Basically the control volume is the initial volume that used for traditional method.
Traditional method for what? For how?
Locust farm.
What is the area?
1 hectare.
1 hectare. So it's for 1 hectare. Okay, good. Then you should put that one in your engineering target, because when you say 50% is not the same. If I do 50% for 1 hectare, and 30% for 1 tree, I will design a different solution. Or for 10 hectares, I have a completely different solution. So that one has to be specified. Otherwise, 50% is very vague, because 30% is relative. 30% to 1 liter, or 30% to 1,000 liter is completely different. So that's why here you put this one, pumpkin 4,000 something liter of pesticide per hectare. So I should to check your 30% based on this. It's not 30% on, let's say, just trying for one cockroach or whatever it is. Okay? So your design has to be specific. That's why the 80%, the 30%, it has to be related. So this 1 hectare of durian trees or whatever should be, that's your design, one of your engineering target actually. Okay, not just percentage of it. You put percentage, but for 1 hectare. Then I can relate. Okay, that's one. So your calculation, just assume you correct that in the table, and then you did here your calculation for 1 hectare. So 1 hectare, can you explain to me this calculation, how to get the 30% reduction? So for 1 hectare, you need 4,000, that's based on what, the 4,496?
This is the current
Current
case
solution.
study.
Okay, the current solution, they use the normal spray water.
Uh-huh.
So they spend that much liter, okay?
So we calculate, we just times the initial one with 0.7%.
Okay, to save the 50%.
Yeah.
Uh-huh.
So then we calculate what is the volume for 1 trees, because we want to design the 9 trees together. So we calculate 1 trees, what is the volume per spray, and we times 9.
So,
We get,
so in that hectare, how many trees of durian usually there are?
so for 1 hectare we have 1 to 5 trees.
One?
1,225 trees.
1 to 5 trees, okay?
And then over below that, this is just the input and output flow rate. So
So you need a 257 liter per tree, right?
yeah.
Based on your 50%. And then you design here, what did you design here? Which component are you designing here?
So basically, this is we get this to get the flow rate, and for the flow rate, then we get the cost the pump.
Okay, next, then show me next how you use the flow rate.
So using the Bernoulli head formulation, so this is the initial, but this is the only one we calculate because the answer is 0. So we calculate the velocity using the flow rate Q is
Okay, so find, at the end you find the pump. Alright, I'm not sure about this one. Probably I can check that one. But this one, okay, so the flow is correct at least. I'm not sure about the quality of the equation. Alright, so we find the pump. How about the other component?
So next is the tube. So basically, yeah, if we get the flow rate, we can get the inlet and outlet flow rate. So we calculate the maximum pressure using axis of the fluid.
Why answers? Why don't you just, because here you have to design this tube. How do you decide on the unit, on the size of the tube?
So
you have the flow rate, you have the thing. So basically you just decide on either the length or the diameter or whatever of the thing. You have to find it, not by answers. Answers you can use it just for validating or for verification, not for the design.
but we want to calculate the maximum pressure so that we know what tube is okay to cover our product.
But before that, because to find the pressure you decided on the tube already. You gave the diameter, you gave the length, you gave the thing. So how do you know that's the right tube? That's my point. So first you have to design this, the pipe, then you can check, I don't know, the pressure or whatever, if it will withstand or not withstand up to, because I don't know why you're trying to do the pressure anyway. So if you design it,
So basically we need the length of the tube is 5 meters, which is based on the tree, which is the average tree is 7 to 8 meters. So we basically put the rope is 5 meters, then we determine the diameter of the rope is using flow rate.
where do you see the calculation? Because here you show me answers and color. This is not, for me, is nothing, this one. You know, you don't impress me by putting things and give me some color. I know how it works. Okay? So my point is here is you have to design the same you did for the pump. You have to decide on this. If you say the flow rate, then since you have it from your engineering target, let's say the 5 you said because I need to cover the thing, so I'm going to fix the length to 5. Now let's find the diameter. And then you do your calculation, find the diameter. Then you find the dimension of your part. Now you want to verify with answers, go and play with answers. Okay? Check the pressure, check whatever you want to do. Okay, but at least now I know that you identified the part. The other components? Any other components in your system? There's many components. Can you go back to your design? Yeah, all this. How did you find all these guys? The battery, this. How did you decide on those?
This is just for proof of concept only. But later for example, for this we have two different matrices like DC and AC. But at first we want to create it into one, but it's too hard for us to think. So we just.
So what is your prototype?
Yes, exactly.
What is your prototype?
Any reason you cannot bring your product here?
Because it's too big for us.
What is it? What is it? I want to see it first. So there's a pump. And then what else?
Yeah, your design analysis you are going to obtain 0.067 horsepower of pump.
So yeah, but at the market the lowest you can find is 0.5.
Yes. You buy it, you bring it, you obtain it, the pump. Where is the pump? Where is the tube?
Okay.
So everything our product is at Mahala, so
Why you can't bring?
Okay, show us a picture of your prototype. Please, let's see a picture first, then we'll see later. That's the nozzle. That thing that you are all hanging to attach, how are you going to attach it to the pump?
So we hook using C-hook and then we nail it to the tree.
So every 3 you have to do that?
For one system, yeah, one system is 90. One system of 90.
So it is like it's open, then you just close it along the tree and apply it or something? You say the time stuff to do all the stuff. And what is the length you decide on the tree?
So our target trees is basically the medium and large trees because they are the most that produce
Okay, what is the last
So
tree?
the length is 5 meters.
Okay, the one where you put this one?
The length of tree is 8 meters and 9 meters like that. So we want to put it at 5 meters.
So how you put it at 5 meters? Now you put it like you are on the ground. You put it. Are your length is 5 meters? Your height?
By the video we just get down the height to just 2 meters, so that we just
Yeah. So how do I know you're gonna reach the 8 meters from there with your nozzle, with your pump and stuff? Your validation doesn't make sense. If you scale down your things, 2 meters or 1 meter, then you do 3 meters, and that's by your calculation. If you do that with this pump and stuff, so if you use the right component, you can achieve the 10 meters. Then I can accept. But here, I don't see the thing. And your validation, a lot of numbers, but I don't see anything. So how am I going to trust your numbers? All these tables? Since you didn't show me how you did the calculation, since you didn't show video, the prototype in front of me that I can see, then you put number, achieve 30%, achieve 80, achieve. Just pick one table, and I'm going to stop here anyway. I said I'm not going to talk too much, but just too many things there to question that and not skip like that. So just give me one of the tables, like the 50% or 80% or whatever, that the validation, okay? Any table. No, not this one, validation. Like this one, okay? So how you did this one? The test?
So we set up the host to the one tree, and we put the container at meters because our design is at meters here and this left.
So the container you put it in the tree?
No, on the ground.
On the ground.
This is just to make sure that the bilateral the spray can cover the area. So then we find out how many insects die.
Yeah, but is that realistic? The insect usually they are in the tree, right? The insect in reality.
How
Still lagi kita spray kat atas kan?
but we still spray, we still hang our product at the top of the tree. Not at the top, but hanging it up there. So if they can kill at the ground, so they can kill at the top.
Yeah, but now you have your container there. The insects there, they are in the container. Maybe they will. The more you think, they will fly away from your insect, and then they get survived. When you put them in the container, they cannot move. Anyway, my point is, it's not realistic, exactly the same condition. That's one. Second, those insects, are they the same insects that they are in the durian? Cockroach? You have cockroach in the durians? Cricket. So those are the same insects from the durian?
One of the best.
One of the best. Okay, at least that one, fine, if you manage that one. And then here you say like, whatever. So then there's no escape for them in the container. They cannot escape from the container, right? So you spray until they die. Anyway.
Because they want to show that at least the spring system can reach those areas.
Okay.
So maybe that's why they put it. That is different.
So this for the insect. How about for the volume? The validation for the volume or another validation?
So this is basically just we measure the initial before we spray and after we spray. So what is the difference, and then we compare to the traditional.
The time taken. What is the time taken here?
I'm sorry, that's from the before. So this. This is the volume. That the time is another one.
So how do you calculate the volume? Your volume?
So basically the nozzle to spray, we not gonna open the nozzle to the surrounding air. We just cover it with plastic, and then we calculate the volume of water in the plastic.
No, but you want to reduce this based on what? The percentage. So based on the current solution, the current they use this, you use this.
Yeah.
To do what? For what? For 1 tree, for 5 insects, for what? What are you trying to do here? What are you comparing?
Per system, right?
For one system like this.
So this one for 9 trees, they will use 367 liters. For you, for 9 trees, you use 2 liters.
Oh yeah. 2.5.
Yeah, but I mean, this is based on calculation or based on testing? This one?
So this is based on testing. However, we also try the calculation. So we find the suitable pump with the flow rate. So we control the flow rate.
Oh, the final volume here, how did you get that? 2.479?
From the testing.
The testing. So
But testing what? Did you test 9 trees?
That's one system. For the control volume, we take from the case study. We have some lesson. So they already put there for 1 liter. So for 1 hectare, how many liter they use?
is it according to the 90s?
See, this one you say validation. So that means what? I have this, okay? I know from the current one, if they cover this based on the calculation, whatever, 367. Now I design my solution, right? So I need to kill the insects in 9 trees for whatever the things I have to give them. And then I see that, okay, now after these 9 trees with my system for thing, I found that it is 2479. Then, okay, that's kind of validation. Here I don't see your test it doesn't show what are you testing. Can you show the graph, the image, the plan, the trees, the drawing? Just you give me numbers, I can put any numbers there. Okay, I'm not saying you're cheating, but it's not convincing for me to see it like this. Because like I said, I can put any number and I get the 50% back. But at least I need to see how you did the experiment. And then for the experiment, you showed me the measurement. Okay, this for 1 3, you measured this volume or this. Now 9, now it is this. Then okay, then you can put it in the table after that.
So for this actually, we take the first one, the control volume from the previous study, which is 3.67, and we put in our container. And then after that, we're gonna spray it about 10 seconds. So after the 10 seconds, we recalculate back what left in the container, and then we get that the only volume that we use for our system is only 2.479 liters, and then it shows that it has reduction for 33%.
Okay, fine, I like that. But again, the one that you spent, the 10 seconds or whatever, what is that? Is that, your validation should not be by calculation or by assuming. It should be testing. You have your prototype, now you test it in reality, and then you get what you get. Okay? Validation doesn't have to be calculation anymore. If it is calculation, that's not validation anymore. Alright? In our case, at least, validation, since we go for prototyping, then we have to test the prototype on real condition that it was designed for, and then see if I achieve those targets. What you said is correct, probably that's how you should do it, but you should show that volume, you put it, you get 9 trees, you have the amount of insect you need to get the area, you spray that area, and then you measure. What is left for this much, so then I achieve or not. Okay? I don't see the test on this. But you need to bring your prototype. Anyway, big or not big, I mean how big it is.
3 meters to 1.5 meters.
No, but 3 meters, the other is not, is it a pipe or you use a hose?
Use a pipe.
A pipe.
Pipe.
5 meters.
Yeah.
Huh?
Yeah. And then there is pipe from bottom, there is pump, all the systems are in the ground, and also the container. And then there is a pipe about 2.5 to 3 meters up there. And then there is a ring.
Okay, then you bring it maybe not to the room, but put it on one of the trees. Okay, on the parking, and then if they want to go see it, the judge, they can go there. But you have to show the prototype. Okay, there's many trees there. Just put it on one tree, maybe not the 5 meter, even lower, but at least then they can see the prototype. And then you can explain from there how you did the testing and validation stuff. Maybe better than giving table. For me, table, like I said, if I don't see the experimental setup, then the table, the number I don't trust. Okay? Or I don't understand, not trust, but I don't relate. All right, thank you. Group 4, the parts that were not designed for your prototype, no need to put in your presentation. You'll be liable for it. It's our examiner, there for industry, and say, oh, the battery, the circuit, well, and then you say, no, this is for future plan. then don't put it. Leave it in the future plan. Okay? Otherwise, they will judge as if you put it in your design but you didn't achieve it. It will work against you.
Assalamualaikum warahmatullahi wabarakatuh. Welcome to my briefing session for Positive. So we are group 6, the group fitness supervised under the next. So what is our problem? So the problem is that the heading drivers, particularly age 50 and above, confront with low back pain. So we come up with our solution. Next. Proposed solution is positive. First is to provide number spot. Second is to ensure posture correction, and third is to dampen the vibration effect of the car. So it complies to ISO. And next. So this is our benchmarking. So as you can see, our positive cover all the three requirements. So meanwhile, all these benchmark are not the next. So this is the CAD model and the sketch of the positive. The next. Okay. So for the first reasonings, we aim to provide number spot, and our engineering target is to follow the lumbar curvature with minimal deformation under load. So the load is 10% of 75 kilograms for average Malaysian man at 160 centimeter. And then second is posture control. So we aim to ensure posture correction by making sure the seat is angled at 10 degree. This is validated. This is suggested or recommended by Dr. Zaki Solihi, our interviewee. So the third is we will avoid this degeneration by the vibration patterning. We aim for 2 phase. Next. So this is should have and could have. The first is user friendly, and the could have is easy instruction. Next. So this is our baseline. This is dimension. This is Pro 2 Saga sedan, which is the most common e-hailing car in Malaysia. So this is the dimension for the seat only, but this is overall. So we manually measure it, and we take the simplification, which is the seat area is 45, then 40, and then the rest is 40 times 50. Okay, next. So this is the design analysis for the first engineering packet, I believe. Okay. So 3 centimeter is the depth, the protrusion. Okay. So that's our aim. So we also need to ensure the deformation is only 3 millimeter threshold. So this is the calculation, and then we also get the contact height. So this height and width. Okay, sorry. The width is from the dimension. The height is the recommendation from the TVV. The contact height is also the recommendation, and also we got the correct. And also the test is also the recommendation from the executive to follow the LAPA convention. Next. So this is posture control. So the aim is simple. We need to ensure the degree of the seat is 10 degrees. So we calculated the end seat thickness here to be 8 centimeters. The next. So this is vibration deepening analysis. So the formula is only natural frequency. We aim for 2 Hz and 30 kilogram mass because because it is stated in article that only 30% of the only some percentage of the mass effect load on the seat and other effect on the parents. So the calculation only focus on the seat. So the thickness of the seat, and for that we use the similar value for the parents as well. So we got the value is 12 millimeter and 12 for foam and 2 for silicone. But for our simplification of configuration, we make it 2 centimeter and 1 centimeter. Next. So next. Okay, next. Next.
There should be a video here, or can we do the internet?
So by making the prototyping process is simple, we bought the foam and we glue it together and we stitch it together. And okay, let's cut also. Some part we are managed to so for the first validation is to make sure the information is the 3 millimeters, so it's easy enough, but it's not reliable because we do it by eye only. So the inclination angle is 10 degrees using inclinometer. But for the vibration validation, there is some issue. I think the first is that we test it without the mass, the person itself. Second is that maybe the sensor from the phone is not accurate enough. Or third, maybe the sampling rate. So we need to try again on that part. So it's okay, that's all.
Okay. So what is the problem again? Can you go back? I want to link the problem to your design spec. I want to see that. Low back pain, okay? Then
the vibration effect on the spine.
then the vibration effect on the spine. Then that's all.
And also issue is that the driver posture is very varied throughout the drive. So that's how the Sakala class doesn't have this inclination, so we need to add that.
Okay, can you donate your design spec to see how you're trying to design for this? Okay. Provide lumbar support and achieve lumbar structure design follow lumbar solution the minimum deformation rate under 10% of user load. Okay? How's this one linked to the pain relief?
So the lumbar support itself, as validated by our interviewee, the support will have its ergonomic curvature. So
No, we're talking about the solution now. The support. My point is, use the knee now, I'm driving, I have pain. Okay? Now, what is the target here? Now, I want to have zero pain. Alright? Or I want to have, reduce my pain by 10%. I don't know, whatever. So, what is that? How is this? When you put minimal deformation, 3 millimeter under 10% of user load, that will reduce my pain relief or eliminate my pain relief. What is the name? Can you explain?
So minimal information is that the lumbar support is working. So yeah, it provides the correct amount of support to maintain the curvature of spine. Yeah, but I get the point. Maybe we should.
I think I mentioned this before also. Number 1 and 2 for me they are solution based. Unless you convince me that 3 whatever minimal deformation with lumbar curvature under 10% of user load, that is whatever medical things they found, if you have that one with certain support, then you won't have pain relief. But I don't see how that anyway. If this, then okay, I can get it. Otherwise, for me, it's a solution thing. I'm going to put the support, and then I decide to whatever who said 3 degrees or based on what, I'm not sure. So I have to see if that is direct link to the pain relief. Similar for the 10-degree inclined angle seat. I decided already my solution. I'm making a seat, I want to incline by 10 degrees, then I have a good posture control. How that 10 degrees is coming from where? Or who decided on that is a good posture control? Is it standard for that? I don't know how to make it as my engineering target for my design. Unless for posture control. Whether this should be like my posture should not this, should be this, whatever. I don't know if they have some ergonomic things for a good posture. Then probably that will be my engineering target. I'm not sure again what is this, but for me this is solution specific. You have your things, you want this angle, you want this, which anyway, it decides based on your solution, not based on the user needs. That's the impression I get, unless you convince me otherwise. Okay? And that's why your design analysis is kind of straightforward. You don't have much things, especially for the first two. It's just geometrical. My seat is here, so I put this one, alright? The angle 10, then I get the thickness, alright? You know, just the tangent. Which, again, I'm not sure if it is the right approach. The first one, I don't even know how you achieve the first one. That, whatever that thing, you can show the calculation again. But is that, you can show that I won't have pain relief? Because your validation, how do you validate this one? Again, by measuring the 3 millimeter and stuff. But how do you know there is no pain? Did you have someone who tried that one and drove, but then for whatever time he said for 8 hours work, and then he came out, okay, I don't have pain compared to previous. For example, at least. Then I can see. Same for the poster. Using your seat, then he drove for whatever the period before that causes him trouble. Now he does the same thing with your prototype, then he doesn't have.
So we should somehow measure the pain before and after using the product.
I mean, based on your user needs, he said pain relief, so I want to see that your solution now is relieve my pain. But by doing, again, you do calculation here to find the component, and then you do calculation to prove that one. For me, it's not prototype validation. Yeah, that's. So for the frequency, also you didn't do the test.
The validation is
No, both. Even the first validation for me is not validation. By the way.
okay.
The validation you do show for number 1 and 2, they are not validation.
Oh, okay.
For me, it's not validation, it's verification. You can call it, but it's not validation. So you verify your calculation in a sense, but you didn't verify on the user that he has no issue with the poster anymore, he has no issue with paying, etc. That you solve those issues. I don't see there because you didn't test it on a user. Okay? Because this one is like ergonomic problem, so it should be tested actually by user. Replicate the same conditions of work or whatever, and then measure, even if it is not measurement accurate, but at least qualitative. Then they will tell you, you know, I used my Saga without this yesterday for 8 hours or for whatever, this e-hailing, or for 1 week or whatever, when it happens to them. I had pain relief, post control. Now I use the dual for 1 week, I feel better. Less pain, my posture is better, I don't have pain here and there, so it looks like it is working. So at least qualitative. Otherwise, I don't see that you achieve it actually. I mean, you are convincing to say that it is working. Okay. The vibration also the same, that means you have to put it there and you see also to see that how that accumulated. But this one should be easy, I know, because you need to measure the frequency, right? I mean, easy in the sense you have to do a shaker or something, I don't know how, but when you have a gate or a automobile, I think they know how to probably measure that one. Anyway, but at least that one, okay, the attenuation, because this I think we discussed before. We said the 2 hertz is the one that doesn't, whatever, it's acceptable and whatever it is, based on standard or whatever it is, medical thing, it's fine. But now we have to show that when you put this one and the Saga is driving, that your frequency is actually 2 hertz, so not more, not less. Alright. Group 6.
Okay, Bismillahirrahmanirrahim. Assalamualaikum. So we're from Group 9. We would like to introduce our product. A little background from our product is because of one of our friend, his father has gone through undergone the sternotomy surgery where he had his chest cut open. So to recover his pain, so he need to wear a chest braces that give him like 3 problems. So the first one is his body temperature increases, which lead to the second problem. He had a skin irritation, and for the last one, he also had a chest pain when he coughing or sneezing. So our solution, we come up with our product. Chassis, so it's designed to chest brace aimed at post-sternotomy recovery, focus on providing optimal sternum support and preventing skin irritation. For the first one, we use the low friction material nylon polyester to encounter the high body temperature, and also we add the special mesh to maintain the skin temperature to reduce the skin irritation. And our focus is for the sternum support, where we put the TPE gel on the center of the chest breast to reduce the force distribution, to reduce the chest pain when it's either coughing or sneezing. So the next one. So this is our design specification table. So first, usually we focus on optimal sternum support. Like I said, we use the TPE gel. So our engineering target to reduce the sternum pressure by 70%. And the other usually we focus on the skin rashes and irritation. So we use the material nylon polyester to reduce the friction coefficient and skin pressure to below 200 Pascal, and also to maintain skin surface temperature below 34 Celsius. So this is our 3D model design, the chassis. So we focus on 2 systems, support system and also the comfort system. So our input is for to reduce the external or internal force like coughing or sneezing from inside. And also the body and surrounding heat when the patient use the chest braces. So we use the TPE gel and also the nylon polyester to reduce, like I said, to reduce the sternum stress and make the chest braces cooler, so that it way more comfort. Way more comfort for the patient to wear it for a long period.
Assalamualaikum. As my brother mentioned, the support system and comfort system. For the support system, we are having sternum padding, like we use TPE gel. This is the heart of the support system. This one function is absorb and redistribute the force. So we got from the stress equation, like which area we needed for the TPE gel, which area mostly need to cover. Our main target is force attenuation is more than 70%. So, and another thing, we need the area 0.0225 millimeter, and based on the safety factor in the medical device is 2. So we saw the stress field versus our stress came 52, which is very less than 20 milliampere to 50 milliampere. So, and about the comfort system, like when it's skin rashes or the temperature, we mostly follow the our main function is minimizing skin contact, friction, force and pressure. So we choose the polyester fabric, and also we choose this pressure mesh to increase the airflow. You can see the nylon polyester friction coefficient is 0.2. So when we got our pressure got 16.9 pascal. My brother mentioned less than 200, so it's very less. And about the airflow, our main target is reduce the temperature, reduce heat buildup to skin, reducing discomfort and rash. So the body temperature we need less than 34. So in this process there is a convection and convection. So the total temperature thermal resistance will be 34. So it will be around our expected temperature. So there will be less skin rash and comfort will be more. This is our programming process video. So we got three test cards for our engineering target. Test card 1, force attenuation mechanism. So we use the PPE gel to increase the force and to redistribute the force. To verify that, we will put weight on a surface with and without the PPE gel. Our concept work is defense of the measured pressure 70 kilopascal. And this got 2 thermal regulation. We use thermal sensor from the inside. This one is our vibration laser table.
Alright, it's group 9. Okay. Can you go to your design spec? I think the problem okay. I want to see the alignment again. So you have the force, you have the skin rush, and that's all right. Okay. Reduce cranial pressure by 70%. Why by 70%?
Based on our research, there is enough sufficient, there is sufficient reduction to reduce the sharp pain during recovery in skin.
Yeah. Based on what 70% of the pressure on the string.
Yes, 70% of the pressure.
But how? What is the pressure of the string usually? Like when the cough, is this during coughing or during what? Because when you say 70% of pressure depends on the original pressure.
Yeah. So the cost from the specialist, the cost from the coughing is 588 for instance.
That's from the coughing?
Yes.
Okay. No, this is, we go to this one now. Go back to the other table. So that's why you have to be specific here. So attenuation of international forces, not example coughing. You do is coughing the worst case?
Yes. Is the peak internal force.
Yeah, so it's the worst compared to other whatever things. Coughing, when he coughs, that's the most pressure he gets from the string.
Yes.
Then you have to put it there. Reduce string pressure during coughing by 70%. Then I know why you have 70%. The coughing is the highest, whatever, by reducing by 30% of coughing should be accepted. Okay? Alright. The comfortable, I'm not think it's comfortable material. I don't think you're doing designing material, but anyway, fine if you do that. But here, what is the skin pressure less than 200 megapascal?
That is for reduction of risk for the skin rashes. So if the fabric like have
not fabric. Even okay, fabric or whatever. So skin rash, if I have a pressure, something with pressure on it, if it is less than 200 pascal, then it shouldn't cause skin rash.
Yes.
Based on some medicine and stuff. Okay, that's good. So then, I don't think you need to put the friction coefficient, by the way. Okay, because this, how you get that 34 feet less than 2?
That is standard private area.
No, because then you pick it already the polyester as your material. That's why you have 0.2%. So it's solution related, you shouldn't put it there. But maybe you do your calculation, then you find from that the friction should be less than 2, then I pick polyester, because it meets there. So it will be part of your deriving thing, but not your because this is specific to the solution, it shouldn't be like that. But the pressure is fine if it is true what you say, right? That based on the medicine, less than this, it should be less than scale rush. The last one, the temperature, maintain skin surface temperature below 34, right?
Since I don't irritating when it's more than 34, such as when you got fever. And
No. That's what, based from where you get it? Similar to the previous one. What did you get? How did you maintain temperature regulation, maintain body temperature below 34? Is this related to the skin rash or the irritation?
34 is like average body temperature. So if we should maintain it below or
No, 34 is very cold for body. Imagine your body temperature now, I don't think it is 34. Maybe 37 right? If you go to 38 point something, you have thought that's fever. Anyway, it doesn't matter. But my point, what is this 34? Where you get it from? As engineering target? Is it just you chose the number like that? Because it has to be related to your needs, which is the skin rash or irritation. Some comfort or whatever, that 34 should be the temperature of, I don't know. But anyway, so that means you're cooling your skin actually. You're cooling your body temperature.
it should help the body to dissipate heat from the, like the body generate heat. So that the skin temperature should be.
That's why I think it's not right that the engineering target to be put like that. First, not right. Second, I don't know where you get it from. Is it again some study like you mentioned before for caffeine is the highest based on the medicine, and 30% of that shouldn't create a problem on the open chest? You know, that okay, and I understand. So your design has to meet those standards, or those known values. That the last one should be the same. It's related to what? The temperature. Is it related to skin, to irrigation, to whatever? And then you have to get again where you get that one. Maybe like you said, dissipate. So it's not actually to maintain 54, but dissipate, I don't know, 5 degrees, or get it close to the room temperature. I don't know what. You know, so then to be comfortable. Then you don't have irritation, for example. I'm not sure. Then okay, then it will make sense. Okay? That's what you have to clarify. Now just show me your calculation, one case. I want to see, for example, the first case. Alright? So this one, the 60 kgf, that is the coffin. But that's nothing. You have to put there. You have to put the coffin. Okay, so no, but the internal force, I don't know, it's coming from where, internal force, right? So it has to be from that, since you put coffin there, then coffin. Okay, so that will be the coffin force, which is 60k, right? Force which is equivalent, let's say, close to 600 newtons, right? Then, how do you use that one? You want to reduce that by 70%. So you're going to use 30% of that for your design, in a sense. Or you should, whatever your device should reduce that by 70%. Okay? So you have sigma FA.
That is the ratio of stress
On the strenum.
Yes.
So the strenum here, the area?
So that is without the pain. So the area of strenum is 60 centimeters.
For?
The area of the strenum.
So your area, my area, all the same?
That's the average.
Average?
Average for like Asian people.
60 centimeters square. You found it somewhere?
Yeah.
Okay, fine, assume that one, alright, so you have f over a, you get the sigma. Then, sigma attenuated, it will be 70%, so, no.
The attenuation factor should be 30%.
The attenuation should be 70%, right? So that means,
So that the stress after attenuation should be around 36.16 kilopascal.
yeah, so that's, no, that should be the one on the chest.
That is the stress.
After you use the pad.
Yes.
Okay? So then the pad should not, actually is wrong. The pad should be 70%. My pressure, you know, is 100%. But I want my strenum to be only 30%. Because I want the pad to absorb 70%. So my 70% should not be 1 minus, but it should be sigma pad, should be the strenum by 0.7. So the remaining, that 26, that's what I'm going to apply to my strenum actually. It's the other way around. Otherwise, here you reduce it by 50% only. 70% will be applied to your strenum. Since sigma pad only, 30%. So you have to change that one. Okay, your calculation will be actually quite different. Then let's say the L pad you find, whatever that force, over sigma pad. Okay, so you find the area of the pad. So what is the pad here? The white thing? Or no? Or the whole thing?
The white is what?
Just the white part?
Yeah.
Okay.
That's actually the pocket.
The pocket is the, okay, so that is whatever that area. And then, factor of safety, I don't know what. Then, okay, so, what did you design here?
First to find the area of the padding.
You found the area of the padding, very good.
And then for the factor is the reason why we choose TBE.
Okay, for medical is 2, so you multiply by 2 for your stress, okay, but that should be done actually earlier, not now. To calculate your area, you should use that factor of safety before, not after. Okay, to make sure that your pad is, you know, taken into account factor of safety. Anyhow, and then, so, what is the outcome? No. So what is the outcome? How do I know what is the pad now? Just the area?
The area of the padding, yes.
Very good. Okay, this one is 0.045 millimeters square, the area.
Yeah.
But it's bigger than yours. How come?
0.022.
Yeah, but this one also 0.02. Why? Because this is very long, but this thickness is very small. Or whatever, this width here is very small, this one maybe not the width here. Because you do areas. I don't know why area again. Because the area, again, it will be, so that means this one, they are the same according to you. Even though this one is thicker. Right? But the area is the same. So which one I'm going to use? Why the thicker one? You didn't design the thicker. How did you decide on the thickness? So you have to decide here. You can fix the thickness, for example, I'm not sure. And then you find your, I don't know, area or whatever. But the thickness here is not important in your calculation. How?
Based on the fixed thickness. So the thickness is what?
The agent has a fixed number of force attenuation percentage.
So the thickness is about?
The thickness will vary depending on the force attenuation percentage. So we decide which is the minimum thickness.
Which is?
10 millimeter. Because when we reduce the thickness, the force attenuation factor will be reduced. It depends on the thickness. It's property.
No, but the thickness usually is involved with something else in those kind of gel material. Is because they have for a certain thickness or a certain, then when you have the pressure, it will be a reduction of 50 kilopascal by millimeter by whatever it is. That's another property of this TPE. So you have to pick what is the attenuation that you want. Remember, I think we did an example similar to it. You know the shoe? It's kind of similar to that. The example of the lecture. There's another parameter which is the reduction by thickness. Then you can fix. If you fix that one, then you get the thickness basically what you need to by dividing this by that parameter of this TPE, then you get the thickness. Otherwise you cannot. I mean area, but it's so that means I can use this or I can use very thick like this, still the same in your design, which doesn't make sense. Okay? So the last part here, that's what I don't like at all. That's a verification, that's not the design. Your design is to find the spec of your, that white thing, whatever it is. Okay? The area, the thickness, okay? The material you can decide that because that from the thing, whatever they assume or absorb, then it is TPE with this certain properties. But now, since I choose the TPE, now I find its area and things that it can actually get that absorption 70%. Alright, so that one not there to see the pressure rate is less than that and it is good. No. You didn't design here actually. According to your calculation, I don't know why you choose that size. Because from here there is nothing to say that size. Right? You get the area, yes, this, but I didn't get what is, the thickness, the length, the width. Because the area also this one, it can be this one. Still the same area. Right? Very long, but the width is very small. Or I can get square, also area. But which one more suitable for the strength? I don't know. Then you have to decide. Okay? Or by some of your calculations. So make sure you think, you understand when you do things. Not just give numbers. Like I told you last time, not the sake of calculation for the sake of calculation, you give numbers. You have to understand those numbers. Alright, after that, I think that similar, all the others the same. I think it's gonna, you start good, but you finish bad. The finish should be the spec of the component. Like this, thickness, length, etc. If you go to the next one, what is the, this again, it should not be the, let's say the friction. Because what is the 200? Remember you put 200 Pascal? What is it here? Yeah, but you should start your calculation by that. That's your engineering target. It's not involved here. I don't know what you're doing here. Contact area, then you get this weight of prototype. Where it came from? The 0.5 kilogram. Yeah, but how is that involved in calculation of the pressure force that you... So as if it is kind of your engineer, how you decided the 0.5 kilogram as your weight of prototype? That will be done once you specify the component. If I find the pad, area, thickness, then I know what is the volume multiplied by density and the mass. This one, how do you decide that stripe, this area, this, whatever that material, then it has some mass. Then the top. But if you specify already, it becomes as engineering target. That means your user or the doctor said this one should not go more than 0.5 kilogram. It should be light. And that's the maximum mass you should put on the stand. Then it becomes engineering target. Now you have to add it to your table. As engineering target. That means your weight should not exceed 0.5. If it is said like this is not actually, should not be like this. Alright, and the temperature also the same. That one doesn't, again, if it is a variation or dissipation, then you use that as your engineering target and you try to find. For example, from here, what are you trying to identify as a component? Using the temperature, which component to identify? Your spec? Nothing. Calculation, again, for the sake of calculation. Here, let's go back now to your things. Can you go to your drone, the 3D drone of your solution? And then I finish here. Yeah. So here, what are the components you need to design besides the patch? The white patch? What do you need to design?
The padding.
Only the padding, the white one. That's all. So the other nothing.
We need to design it.
Huh?
we design the strength and also the
Where the calculation on volume? And which engineering type related to that? Is that type? It has to be type to a certain level? This one. Or I can make it loose. The black one. Forget the pattern. How tight I should have it? Too tight, so tight, to be for the strength, not to be to create more damage and stuff. I don't know if there is any requirement on that. If it is, then it should be based on your design target, and then you decide what is you make for this one. I have this much pressure. If I type here, I have more whatever pressure, etc. So I make sure that I put some gadget or not some line tight here because we measured that one. That's the 100 kilopascal or whatever. You know, so then it will be safe. Otherwise, you might do all this, but this here I feel it's too loose. That tight more. So then I create more damage to myself. Or to put too loose, then whatever calculation I make for the patch, it doesn't work because it's too loose. So that all the pressure is on. So there are other things that are missing here. You focus just on the patch, but the patch itself is not it is part of the other things you have, and they will affect your solution. Okay? Alright. Thank you. Good night, huh?
The story, I think, is better.
Mm-hmm.
The flow story.
The presentation, yeah. The presentation was so nice, but